Hello students, welcome to this lecture on complex numbers and quadratic equations. In this lecture, we will cover NCERT section 4.4 and we will solve examples 5 to 6 and exercise 4.1 question number 1 to 4. So let's get started. This is disclaimer. So we will start by looking at two important concepts in complex numbers, the modulus and the conjugate of a complex numbers. Then we will solve NCERT examples 5 and 6. Next, we will solve NCERT exercise 4.1. So I hope you are with your notebooks and pens ready, and now let's get started. So now we are going to talk about the modulus of a complex numbers. So what is complex numbers we already know, okay, and now we are going to know modulus of a complex numbers. So the modulus of a complex numbers is a fundamental concept in complex numbers and helps us understand their size or magnitude. So let's start by looking at its definition. The modulus of a complex number z equals x plus iota times y is the non-negative real number, and it is defined as the square root of x square plus y square. We use the notation mod of z to represent the modulus of z. So whenever you see vertical bars around our complex numbers, it means we are talking about its modulus or magnitude. Now, to summarize the modulus is calculated as modulus of z equals square root of x square plus y square, which is also equal to square root of real part of z square plus imaginary part of z square. Here real part of z stands for the real part of z, that is here x, and imaginary part of z is here y. Now we will look at geometrical representation. So geometrically, the modulus represents the distance from the point x comma y to the origin in the argent plane, which is just like the coordinate plane but for complex numbers. Okay, so you can see in this diagram labeled figure 4.2 that the modulus is the straight line distance from the origin to the point representing z. Let's look at an example to make this clearer. Suppose we have the complex numbers z equals 3 minus 4 times iota, and we will find its modulus step by step. So now look at the solution of this example. So here we are going to find the modulus of z equals 3 minus 4 times iota. So given that the complex numbers z equals x plus iota y, okay, and here we have given z equals 3 minus 4 times iota. So what we will do now? So now we will compare z equals 3 minus 4 times iota with x plus iota times y, and then we will find the value of x and y, and then by definition of modulus we can easily find the modulus of z equals 3 minus 4 times iota. So we know that if z equals x plus iota times y, then modulus of z equals square root of x square plus y square. So this is the formula we will use for our example. So here x is 3 and y is minus 4. So we will now substitute these values into our formula. So now let's do the calculation. So modulus of z equals square root of 3 square plus minus 4 whole square. This is equals square root of 9 plus 16. This is equal to square root of 25, and square root of 25 equals 5. So the modulus of z is 5. Therefore, the modulus of z written as mod of z is 5. This means the distance from the origin to the point 3 comma minus 4 in the Argand plane is exactly 5 units. Now, we are going to talk about the concept of the conjugate of a complex number. So this is an important idea in complex numbers and quadratic equations. So we will now see what a conjugate is and how it is written and what it looks like both algebraically and geometrically. So let's start by defining what we mean by the conjugate. So let's examine the definition. So if we have a complex number z equals a plus iota times b, where a is the real part and b is the imaginary part, then the conjugate of z is defined as a minus iota times b. So we simply change the sign of the imaginary part. For example, if z equals 3 plus 4 times iota, then conjugate of z is basically 3 minus 4 times iota. Okay. Now notice that how we denote the conjugate. So we use a bar over the letter z. So the conjugate of z is written as z with a line bar it, which we say as z bar. Okay, so this notation helps us quickly identify when we are talking about the conjugate of a complex number. Here is the equation that summarizes what we have discussed. So z equals a plus iota times b. It implies conjugate of z equals a minus iota times b. Now we will look at geometrical meaning of conjugate. So geometrically, the conjugate of z, which is z bar, is the reflection of the point z across the real axis in the Argand plane. So in other words, if we plot z on the complex plane, its conjugate will be directly opposite across the horizontal axis. So this visual helps us understand how conjugates relate to each other especially. Here is an diagram that shows this reflection. So notice how the original point z and its conjugate z bar are mirror images across the real axis. Okay, so this visual representation reinforces the idea that the conjugate simply flips the sign of the imaginary part. Okay, so moving the point to the other side of the real axis. Now let's look at an example involving complex numbers. So the question asks us to find the conjugates of 4 different complex numbers. They are z equals 3 plus 4 times iota, z equals minus 2 minus iota, and z equals 5 times iota, and the last complex number is z equals 7. So remember, a conjugate is the special form of a complex number that we will define and calculate step by step. So here find the conjugates of these complex numbers. So let's start with the solution. We will go through each number one by one and find its conjugate. So pay close attention to the process, as this is a common type of question in exams. So first, let's see what we have given. So we have given that z equals 3 plus 4 times iota, z equals minus 2 minus iota, z equals 5 times iota, and z equals 7. Okay, so we will use these values in our calculations as we find their conjugates. Now let's recall the rule for finding the conjugate of a complex number. So if z equals a plus iota times b, then the conjugate of z written as z bar is a minus iota times b. Here a is the real part and b is the imaginary part. So to get the conjugate, we simply change the sign of the imaginary part. Therefore, we get if z equals 3 plus 4 times iota, the real part is 3 and the imaginary part is 4. So the conjugate is 3 minus 4 times iota. Therefore, z bar equals 3 minus 4 times iota. Next, for z equals minus 2 minus iota, the real part is minus 2 and the imaginary part is minus 1. So the conjugate will be minus 2 plus iota. Okay, again we just flip the sign of the imaginary part from negative to positive. Now let's look at the number z equals 5 times iota. So the conjugate of z, that is z bar, equals minus 5 times iota. Finally, for z equals 7, the real part is 7 and the imaginary part is here 0. So the conjugate is 7 minus 0 times iota, which is just 7. So for real numbers, the conjugate is the number itself. Now we are going to talk about the multiplicative inverse of a complex number. So this is an important concept in complex numbers. So the multiplicative inverse is basically the number you multiply by to get 1. Okay, just like with real numbers. But here we will see how it works for complex numbers. So let's look at the definition. The multiplicative inverse of a non-zero complex number z, where z equals a plus iota times b, is written as z inverse, or z inverse equals 1 divided by z. So to actually find 1 divided by z, we need to get rid of the imaginary part in the denominator. So we do this by multiplying both the numerator and the denominator by the conjugate of z, which is a minus iota times b. So we write z inverse equals 1 divided by a plus iota times b, which is equal to 1 divided by a plus iota times b times a minus iota times b divided by a minus iota times b. So now we can simplify it. So now let's simplify the denominator. When we multiply a plus iota times b by a minus iota times b, we use the formula for the difference of the squares. A plus iota times b times a minus iota times b equals a square minus iota square times b square. Since iota square is minus 1, so this becomes a square plus b square. So the denominator is now a square plus b square, which is a real number. Putting it all together, we get z inverse equals a minus iota times b divided by a square plus b square. Since modulus of z square equals a square plus b square, okay, and a minus iota times b is basically z bar, that is conjugate of z. Okay, so z inverse equals to z bar divided by modulus of z whole square. Now, so this leads us to an important property, that is modulus of z square equals z times z bar, since z inverse equals 1 divided by z. Therefore, we obtain here an important property, that is modulus of z square equals z times conjugate of z. So this is a fundamental result that you will use often when dealing with complex numbers. Now we are going to discuss some important properties of complex numbers, specifically focusing on the modulus and conjugate. Okay, so these properties help us work with complex numbers more easily. So first, let's look at the property involving the modulus of a product. So the equation is z1 times z2 modulus of z1 times z2 equals modulus of z1 times modulus of z2. This means that the modulus or absolute value of the product of two complex numbers is equal to the product of their individual moduli. In other words, multiplying two complex numbers and then taking the modulus gives the same result as the taking the modulus of each number first and then multiplying those values together. Next, we have the property for the modulus of a quotient. So the equation is modulus of z1 divided by z2 equals modulus of z1 divided by modulus of z2, provided here modulus of z2 is not 0. So this tells us that the modulus of the quotient of two complex numbers is equal to the quotient of their moduli. The third property, that is now look at how conjugation works with multiplication. So the property is conjugate of z1 times z2 equals conjugate of z1 times conjugate of z2. Okay, this means that if we multiply two complex numbers and then take the conjugate, it's the same as taking the conjugate of each number first and then multiplying them together. The next property involves addition and subtraction. So the equation is conjugate of z1 plus minus z2 equals conjugate of z1 plus or minus conjugate of z2. In other words, the conjugate of a sum or difference is the sum or difference of the conjugates. Okay, so this helps us break down more complicated expression into simpler parts. Next property is conjugate of z1 divided by z2 equals conjugate of z1 divided by conjugate of z2, provided z2 not equal to 0. Okay, this means that if we divide two complex numbers, and then take the conjugate, it's the same as taking the conjugate of each number first and then dividing. Okay, again we must make sure that z2 is not 0. The next property is z plus z bar equals 2 times real part of z. That means when you add a complex number to its conjugate, the imaginary parts cancel out and you are left with twice the real part. Finally, we will look at the difference between a complex number and its conjugate. So the equation is z minus conjugate of z equals 2i times imaginary of z. Okay, here subtracting the conjugate from the original number, cancel out the real parts and leaving only the imaginary part multiplied by 2 times iota. Now let's look at the important properties of modulus of complex numbers. First, we will prove that modulus of the product of two complex numbers is equal to the product of their moduli. Okay, then we will show a similar property for division. So let's show that modulus of z1 times z2 equals modulus of z1 times modulus of z2. So let's begin the proof for the first property. So we will show step by step why the modulus of z1 times z2 equals the modulus of Z1 times modulus of Z2. So we start by writing the square of the modulus of the product. So modulus of Z1 times Z2 whole square equals to Z1 times Z2 times Z1 times Z2 conjugate. Okay, conjugate of Z1 times Z2. Since Z times Z conjugate equals modulus of Z square. Now Z1 times Z2 times Z1 conjugate times the conjugate of Z2. Since conjugate of Z1 times Z2 equals conjugate of Z1 times conjugate of Z2. In this step, you can see Z1 times Z1 bar times Z2 times Z2 bar. Okay, and as you know, Z times Z bar equals modulus of Z square. So this is equal to modulus of Z1 square times modulus of Z2 square. Now taking square root, so we get modulus of Z1 times Z2 equals modulus of Z1 times modulus of Z2. Now let's show the modulus of Z1 divided by Z2 equals modulus of Z1 divided by modulus of Z2. Provided here modulus of Z2 not equal to 0. Let's start the proof for this property. So we will use this result we just proved after the modulus of a product. So we write modulus of Z1 divided by Z2 equals modulus of Z1 times 1 divided by Z2. This is equals modulus of Z1 times Z2 inverse, since Z2 inverse equals 1 divided by Z2. This is equals modulus of Z1 times modulus of Z2 inverse. This is equal to modulus of Z1 times 1 divided by modulus of Z2. Since modulus of Z1 times Z2 equals modulus of Z1 times modulus of Z2. Therefore, modulus of Z1 divided by Z2 equals modulus of Z1 divided by modulus of Z2. Now let's look at an important property of complex numbers. The conjugate of a product equals conjugate of Z1 times conjugate of Z2. Okay, so now we will prove it. So let's start by the proof. So we will go step by step to show why this property holds. So let Z1 equals A plus iota times B and Z2 equals C plus iota times D, where A, B, C and D are all real numbers. And here I is the imaginary unit, which means iota square equals -1. Now let's multiply Z1 and Z2. When we expand A plus iota times B times C plus iota times D, we get A times C minus B times D for the real part and A times D plus B times C for the imaginary part. So Z1 times Z2 equals AC minus BD plus iota times AD plus BC. Remember, the conjugate of a complex number Z equals A plus iota times B is Z bar equals A minus iota times B. So conjugate of Z1 times Z2 equals AC minus BD minus iota times AD plus BC. Also, let's find the product of the conjugates. The conjugate of Z1 is A minus iota times B and the conjugate of Z2 is C minus iota times D. So multiplying these, so we will obtain A minus iota times B times C minus iota times D equals AC minus BD minus iota times AD plus BC. So notice that conjugate of Z1 times Z2 equals conjugate of Z1 times conjugate of Z2. hence proved. Now we will look at another property of complex numbers involving conjugates. The statement here is the conjugate of the sum or differences of two complex numbers is equal to the sum or difference of their conjugates. In symbols, this is written as conjugate of z1 plus or minus z2 equals conjugate of z1 plus or minus conjugate of z2. So we will prove this step by step. First, let's define our two complex numbers. Let z1 equals a plus iota times b and z2 equals c plus iota times d. Here a and c are real numbers and b and d are also real numbers, but a and c are real parts of the complex numbers and b and d are the imaginary parts of z1 and z2 respectively. Let's begin with addition. When we add z1 and z2, we get z1 plus z2 equals open bracket a plus iota times b plus open bracket c plus iota times d. And then if we simplify it, then we can write it as a plus c plus iota times b plus d. Now let's recall how to find the conjugate of a complex number. So if z equals a plus iota times b, then conjugate of z equals a minus iota times b. So applying this to our sum, so the conjugate of z1 plus z2 is equal to a plus c minus iota times b plus d. Now let's look at the sum of the conjugates. The conjugate of z1 is basically a minus iota times b, and the conjugate of z2 equals c minus iota times d, which simplifies to a plus c minus iota times b plus d. Now let's move on to the subtraction. When we subtract z1 minus z2, okay, that means z2 from z1, then we get z1 minus z2 equals a plus iota times b minus c plus iota times d. This is equal to a minus c plus iota times b minus d. Again, we know that if z equals a plus iota times b, then z conjugate equals a minus iota times b. Taking the conjugate of z1 minus z2, we get a minus c minus iota times b minus d. So now let's find the difference of the conjugates. The conjugates of z1 minus conjugate of z2 equals a minus iota times b minus c minus iota times d, which is equal to a minus c minus iota times b minus d. Therefore, conjugates of z1 plus or minus z2 is equal to the conjugate of z1 plus or minus conjugate of z2. So I hope this result is clear to all of you how we prove it. Now let's look at another property, that is conjugate of z1 divided by z2 equals conjugate of z1 divided by conjugate of z2, provided here z2 not equal to 0. Okay, so we will prove it step by step. So let's start the proof. So first let's introduce a new variable to make things easier. So let z1 divided by z2 equals z3. Then z1 equals z2 times z3, Now taking conjugate of both sides, we get conjugate of Z1 equals conjugate of Z2 times conjugate of Z3. Since conjugate of Z1 times Z2 equals conjugate of Z1 times conjugate of Z2. Now let's solve for conjugate of Z3. So we divide both sides by conjugate of Z2. So we get conjugate of Z3 equals conjugate of Z1 divided by conjugate of Z2. Finally, we obtain here conjugate of Z1 divided by Z2 equals conjugate of Z1 divided by conjugate of Z2, since Z3 equals Z1 divided by Z2. Okay, I hope this proof is clear to all of you. Now we will look at two important properties of complex numbers involving their conjugates. Okay, another some property. So the next property is Z plus Z conjugate equals 2 times real part of Z. So let's start by proving the first property. Z plus its conjugate of Z equals 2 times real part of Z. Suppose we let Z equals A plus iota times B, then conjugate of Z equals A minus B times iota. Now let's add Z and its conjugate Z bar together. So we obtain A plus iota times B plus A minus iota times B. Notice here how the imaginary parts will cancel each other out. When we combine the terms, we get 2 times A plus 0 times iota, which simplifies to just 2 times A. So the imaginary parts add up to 0 and leaving only the real part doubled. Since A is the real part of Z or real part of Z, so we can write this result as Z plus Z bar equals 2 times real part of Z. So this shows that adding a complex number to its conjugate gives us twice its real part. Now let's look at second property. Z minus its conjugate equals 2 times iota times the imaginary part of Z. So we will prove this in a similar way. So let's begin the proof for this property. Let Z equals x plus iota times y, then conjugate of Z equals x minus iota times y. Now let's subtract the conjugate from Z. So x plus iota times y minus of x minus iota times y. And here pay attention to how the real and imaginary parts combine. When we expand this, we get x plus iota times y minus x plus iota times y. So the x terms cancel each other out and we are left with 2 times iota times y. This means that subtracting the conjugate from the original complex numbers gives us twice the imaginary part multiplied by iota. Since y is the imaginary part of Z, so we can write this as 2 times iota times imaginary of Z. So Z minus Z bar equals 2 times iota times imaginary of Z. Therefore, Z minus Z bar equals 2 times iota times imaginary of Z. Now, let's look at an example. So, in this example, we have to find the multiplicative inverse of 2 minus 3 times iota. So, let's solve this example step by step. So, let's see the solution of this example. Given that Z equals 2 minus 3 times iota. Here z is our complex number where the real part is 2 and the imaginary part is minus 3. To find the multiplicative inverse, we use the formula z inverse equals 1 divided by z. So z inverse equals 1 over 2 minus 3 iota. Now to simplify, 1 over 2 minus 3 times iota, we multiply both the numerator and denominator by the conjugate of the denominator, which is 2 plus 3 times iota, and this gives us z inverse equals 1 over 2 minus 3 times iota multiplied by 2 plus 3 times iota divided by 2 plus 3 times iota, and here this is equal to 2 plus 3 times iota divided by 2 square minus 3 times iota whole square. Let's simplify the denominator. So 2 squared is 4 and 3 times iota squared is 9 times iota squared. Since iota squared equals minus 1, so this becomes 4 plus 9. So the denominator is 13. So this step is crucial because it turns the denominator into a real number. Now we have 2 plus 3 times iota divided by 13, which is equal to 2 by 13 plus 3 by 13 times iota. Therefore, the multiplicative inverse of z, which is 2 divided by 13 plus 3 divided by 13 times iota. Now let's look at another example. So in this example, we have to express the following in the form a plus iota times b. So let's see how to solve this example. So let's start the solution of this example. So given that 5 plus square root of 2 times iota divided by 1 minus square root of 2 times iota. Now multiply numerator and denominator by the conjugate 1 plus square root of 2 times iota, and then we get 5 plus square root of 2 times iota divided by 1 minus square root of 2 times iota equals 5 plus square root of 2 times iota divided by 1 minus square root of 2 times iota times 1 plus square root of 2 times iota divided by 1 plus square root of 2 iota, which is equal to 5 plus 5 times square root of 2 times iota plus square root of 2 times iota minus 2 divided by 1 minus square root of 2 times iota whole square. This is equal to 3 plus 6 times square root of 2 times iota divided by 1 plus 2, since iota square is minus 1. So which is equal to 3 times 1 plus 2 times root 2 times iota divided by 3. Therefore 5 plus square root of 2 times iota divided by 1 minus square root of 2 times iota equals 1 plus 2 times root 2 times iota. So this is our final answer. Now let's look at another example, example 6, second part. So in this example, we have to express the following in the form a plus iota times b of the expression iota to the power minus 35. So let's see how to solve this example. So let's start the solution of this example. So we have iota to the power minus 35, and we can rewrite iota to the power minus 35 as a fraction, that is 1 divided by iota to the power 35. Next, let's break down iota to the power 35. So we know that iota square is minus 1. So we can write iota to the power 35 as iota square to the power 17 times iota, because 2 times 17 is 34 and 34 plus 1 gives us 35. So iota to the power 35 equals iota square whole to the power 17 times iota. Now let's substitute iota square with minus 1. That gives us iota square to the power 17 is minus 1 to the power 17, which is minus 1. Okay, so the denominator becomes minus iota. So our expression is now 1 divided by minus iota. To write this in the standard form, a plus iota times b, we need to multiply numerator and denominator by the conjugate of iota. So iota to the power minus 35 equals 1 divided by minus iota times iota divided by iota. This is equal to iota divided by minus iota square equals iota, since iota square is minus 1. Therefore, iota to the power minus 35 equals iota. Okay, and you can write it as 0 plus iota. Okay, and this is in the form a plus iota times b. Now let's start the NCERT exercise 4.1 question number 1. So in this question we have to express the given complex number in the form a plus iota times b. Okay, and here we have the expression 5 times iota times minus 3 times iota divided by 5. So let's see how to solve this question. So let's see the solution of this question step by step. So given that 5 times iota multiplied by minus 3 times iota divided by 5, and we have the expression z equals 5 times iota multiplied with minus 3 times iota divided by 5. Now let's multiply the coefficients and the imaginary units. 5 times minus 3 by 5 gives us minus 3, and I times I gives us iota square. So z equals minus 3 times iota square. Since iota square is minus 1, so z equals minus 3 times minus 1 equals 3. And we can write 3 as 3 plus 0 times iota. Therefore, the complex numbers 5 times iota times minus 3 divided by 5 times iota in the form a plus iota times b is 3 plus 0 times iota. Now let's look at question number 2. So in this question we have also expressed the given complex number in the form a plus iota times b of the expression iota to the power 9 plus iota to the power 19. Let's start the solution of this question step by step. So given that iota to the power 9 plus iota to the power 19. So first let's simplify iota to the power 9. So iota to the power 9 equals iota to the power 4 times 2 plus 1, which is equal to iota to the power 4 whole square times iota to the power 1. Since iota to the power 4 is 1, so 1 square times iota equals iota. Therefore, iota to the power 9 equals iota. Next, let's simplify iota to the power 19. So, iota to the power 19 can be written as iota to the power 4 times 4 plus 3. And this is equal to iota to the power 4 to the power 4 times iota cube. Since iota to the power 4 is 1 and iota to the power 3 is minus iota, so 1 to the power 4 times minus iota equals minus iota. Therefore, iota to the power 19 is minus iota. By substituting iota to the power 9 equals iota, and iota to the power 19 equals minus iota into the expression iota to the power 9 plus iota to the power 19, we get iota to the power 9 plus iota to the power 19 equals iota plus minus iota equals 0. We can write 0 as 0 plus 0 times iota. Therefore, the complex number in the form a plus iota times b is 0 plus 0 times iota. Now, let's look at question number 3. So, in this question, we have to express the given complex number in the form a plus iota times b. And here we have given the expression iota to the power minus 39. Okay, so first of all, try it yourself how to solve this question and then see solution. Let's start the solution step by step. Given that iota to the power minus 39, and our goal is to simplify the expression and write it in the form a plus iota times b. So we can write iota to the power minus 39 by finding the closest multiple of 4. So iota to the power minus 39 equals iota to the power minus 4 times 9 minus 3. Now let's rewrite iota to the power minus 39 equals iota to the power 4 whole to the power minus 9 times iota to the power minus 3. Since iota to the power equals 1, iota to the power 4 equals 1, so we can simplify further. So iota to the power 4 to the power minus 1 is basically 1 to the power minus 9, okay, which is simply 1. So iota to the power minus 39 equals basically iota to the power minus 3. And let's handle iota to the power minus 3. Remember, our negative exponent means 1 divided by that power. So iota to the power minus 3 equals 1 divided by iota cube. We also know that iota cube equals minus iota, so this becomes 1 divided by minus iota. Now multiply numerator and denominator by the conjugate of iota, so we get iota to the power minus 39 equals 1 divided by minus iota times iota divided by iota, which is equal iota divided by minus iota square. And since iota square is minus 1, so now we substitute here iota square is minus 1, then we get iota divided by minus of minus 1 equals iota. So we can write now iota as 0 plus 1 times iota, which is in the form a plus iota times b. So therefore, the complex number iota to the power minus 39 in the form a plus iota times b is 0 plus 1 times iota. Now let's look at question number 4. So in this question, also we have to express the given complex number in the form a plus iota times b of the expression 3 times 7 plus iota times 7 plus iota times 7 plus iota times 7. Okay, so first of all, try it yourself. How would you approach this question and then see solution? Let's start the solution step by step. Given that 3 times 7 plus iota times 7 plus iota times 7 plus iota times 7. So we have the expression z equals 3 times 7 plus iota times 7 plus iota times 7 plus iota times 7. So we can write this expression as 21 plus 21 times iota plus 7 times iota plus 7 times iota square, which is equal to 21 plus 21 times iota plus 7 times iota plus 7 times minus 1, since iota square is minus 1. This is equal to 14 plus 28 times iota. Therefore, the complex number 3 times 7 plus iota times 7 plus iota times 7 plus iota times 7 is in the form of a plus iota times b is 14 plus 28 times iota. So students, That's all for today's lecture, and thank you for your attention. I hope this lesson was helpful to all of you.